Welcome all of you. Good afternoon. Let me welcome all of you to the webinar organized by the Department of Chemistry. It's a series of webinars that we have been able to conduct thanks to participation and also the enthusiasm of several of our colleagues. And this is now the third or the fourth, I believe, the fourth one in the series of webinars that the department is now conducting, and I welcome all of you, and also I have the privilege of inviting Dr. Sankaran Subramanian, also former professor and the head of the what was then known as the RSIC, but later it was the Sophisticated Analytical Instrumentation Facility, SAIF. Professor Subramanian has been associated with us for more than 40 years, one way or the other, as a faculty and later as visiting faculty here. And currently, we also have the privilege of having him as the adjunct faculty in our department since a few weeks ago when our department recommended that he should be considered. So it is a pleasure to have him join us as the adjunct faculty and then deliver the first seminar that he would like to give. And let me briefly introduce him to all of you. Every one of you know him well. However, as they always say, as I have said in the previous meetings, our guest, our distinguished speaker is very well known to everybody. He doesn't need an introduction, but he deserves one whenever he decides to appear. Therefore, it's important for me to introduce him also from the chair of the department. Professor Subramanian, who is an FNA and the FASC, is currently adjunct professor in the Department of Chemistry and also with the Sophisticated Analytical Instrumentation Facility. Professor Subramanian, you have to tell me what is FIES. I missed it out. What does that mean? I didn't know anything about it. What is FIES?
International EPR Society.
Fellow of?
Hello?
Probably
Yeah.
the International ESR Society or EPR.
Ah, okay,
Society.
okay.
Is that right?
No, I didn't know. I mean, it's all
I don't
right.
know. He should say.
He will be able to explain. What is the expansion of FIES, fellow of? Okay. He did his undergraduate and postgraduate degrees in Kerala University in Kottayam. And later he was a scientist in Bombay Atomic Research Center, Bombay, before he moved on to do his PhD in the University of Leicester in the electron paramagnetic resonance. He was also a postdoctoral fellow in the same university and later moved to Michigan State University, East Lansing, I believe, on EPR and OpenShell NDDR. So I'm going to mute all of you for the introduction. I'm sorry. Okay. Yeah. He became an assistant professor of IIT Madras in 1971 and continued there, and later became the professor of chemistry and was his area of main research being mainly in EPR, NMR, and theoretical chemistry. He established also the first regional sophisticated instrumentation center in IIT Madras from the DST grants, which now is serving so many hundreds and thousands of scientists and students all over the country. He was, of course, a recipient of the Alexander von Humboldt Fellowship and also the Dart Fellowship, has been a visiting fellow and in NIH for developing 2D NMR methods, and later in the National Cancer Institute for many years, and returned to India as the INSA senior scientist later, and now currently is the adjunct professor. Has guided many students and many MSc dissertations and more than 200 papers in peer-reviewed journals of all very high quality and frontline journals in the field of magnetic resonance and instrumentation, and has also more than a dozen of approved US and international patents in EPR imaging. He co-authored the book with Professor Chandra Kumar on modern techniques in FT-NMR, and the later has...
Sundar,
oh, sorry, correct me.
your voice is breaking.
My voice is breaking. Ah.
Yeah.
Now, is it any better?
Yeah, right now okay, but make sure that, yeah, please go ahead, Sundar.
Okay, I will say rather slowly. Let us see if that helps in any way. He is also he has also written several book chapters and reviews, and was elected the Fellow of the Indian Academy of Sciences, Bangalore, New Delhi, and the Fellow of the International Society, EPR, that is ESR Society. I think that is the FIES now. I see that only fellow from India. And he's a member of the Ampere Society, Zurich, and president of the National Magnetic Resonance Society of India from 2019. And has, of course, several technology development and innovation awards from the NIH in the United States. It is a great pleasure to have you here, Professor Subramanian, to deliver a topic of your choice and expertise that you have given. And we look forward to it, and we hope that the students and the faculty and all the visitors will benefit from your erudition.
Okay, thanks a lot, Professor Sundar, for a nice, detailed introduction, of which the material was given by me. And I sincerely thank you for giving me the opportunity. These webinars in these days of lockdown and COVID-19 turns out to be very interesting and productive exercise, because every week we can have a good speaker and people can sit back at home or wherever they are and listen. And it is going to be pretty effective, rather than trying to ask people to come to a lecture hall. They can sit wherever they want, they can wear whatever they want, or even don't wear anything, and they can listen to it from their Zoom or whatever. So I once again welcome all the people who are online, and let me start this. I have again to thank Mangal for not only arranging this. Yesterday he trained me how to operate Zoom, so I hope I don't make too many mistakes. So as you can see, the title of the talk today is Dancing with the Electrons. And basically it's electron spin resonance imaging and indirect electron imaging, with some implications in cancer research. And let us, Dancing with the Electrons is a title which seems to be a little odd. You can dance with unpaired electrons because they are single, so you can pair with them. Magnetic nuclei, and if you like, with the lovely dancers from all over India. It is the precision and the gyration that matters. Come, let us dance. And this is again a repeat of what I wrote. So you can see the title is fairly apt. These people were gyrating in Earth's magnetic field, while we are going to discuss and investigate the gyration of electrons and magnetic nuclei, ESR and NMR, and then how to locate how they are distributed and whether we can use it for some useful purposes. So I would like to start this seminar by dedicating this webinar talk to my following role models. This was my professor at England who gave me the scholarship, my postdoctoral professor Max Rogers, then Professor Silescu, who entertained me with the Alexander von Humboldt Foundation Fellowship, Becker, who invited me to National Institute of Health for learning NMR, and then Professor Pilbro and Klaus, who taught me a lot about pulse DPR, and they also were in IIT Madras giving series of lectures. Professor Ernst, who visited a lot of times and more or less enthused myself and my colleague, Professor Chandra Kumar, to write a book. Dr. Adrian Bax, who was my colleague in NIH, taught me a lot about pulse NMR and multidimensional spectroscopy. And to two of my dearest colleagues who are no more with us, Professor P.T. Manoharan and Professor Surjit Singh.
Narayana.
I'm dedicating
That
this
option-
webinar to. Now, let us go to the topic, functional physiological imaging. And this functional imaging, X-rays, CT, MRI, magnetic spectroscopic imaging, weighted imaging, both various types of varieties of imaging, positron emission tomography, infrared imaging, ultrasound, all these are clinically approved diagnostic techniques. EPRI, which is electron paramagnetic resonance imaging, is still an evolving functional imaging tool.
So,
And you
Subbu,
can
for a
see
minute.
among the radiological imaging, MRI is capable of producing vivid, highly resolved pictures. As you can see from this, you have a lovely image of the brain stem and the spinal cord. This is an image of a knee, full spinal cord here, and this is the image of the lungs. And when it is filled with hyperpolarized helium, you can also see the chambers where the gases normally are there. So MRI is one of the most wonderful physiological diagnostic technique. And you can see here, this is the diffusion constant imaging of the brain, where we are looking at connecting the unique axis of the diffusion tensor, leading to what is known as diffusion tensor tractography. And it's a great help for neuropsychiatric research for connectivity of synaptic connectivity. Not only that, we can also do movies in MRI where you can see the baby just about a month before coming out is doing all the gymnastics in the womb of a mother. It's amazing that you can do with MRI. Now, why then, if there is such a wonderful technique by way of NMR, what is the big deal of going into ESR imaging? Although electrons and nuclei, paramagnetic nuclei and electrons behave similarly, except the dynamics are different. Frequencies of precession in a given field are orders of magnitude different. And on the top of it, we don't have any unpaired electrons in the physiological system. Even if they are very short-lived. So why do you want to go and toil yourself to develop methods of EPR imaging, and how do we do it? So EPR deals with free radicals, systems with unpaired electrons. The concentration of free radicals in vivo is pretty low, of the order of millimolar or micromolar. Often, many of these radicals are short-lived. So if you want to do any EPR imaging in vivo, we have to introduce stable, non-toxic free radical into the animal system, which should also have a reasonable biological half-life so that we can monitor the distribution. Why should we do it? The idea is tumor. I have to give a little story here. As I was doing a sabbatical in the National Institute of Health, developing multidimensional NMR methodologies, I was having a lunch with the director of Cancer Institute, and somebody introduced me that he is working in the Arthritis Institute doing some NMR, and he's also associated with the in vivo NMR center, where he's looking at the imaging and all that. So the person who is the deputy director of Cancer Institute said, Subbu, can we do ESR imaging? People are talking about MRI. Can we do ESR imaging? I said, why are you interested in ESR imaging? He said, look, electrons, when there is oxygen in and around the electron, they get relaxed. Therefore, it may be possible to map out indirectly oxygen in tissue. And this is very important because most cancers, any type of cancer or growing tumors, they have a hypoxic core. Almost partial pressure of oxygen of the order of 0 to 5 millimeters of mercury. Hypoxia and anoxia alters the tumor cell biology and physiology. And this alteration of the physiological function in presence of hypoxia or in the absence of oxygen can lead to activation of signal transduction, gene mutation, apoptosis, angiogenesis, etc., leading to tumor progression. Therefore, it may be a possibility that we can do electron imaging. Do you think it is possible for us to venture into this? I was on a sabbatical and with another 3 or 4 months to get back to India. And I told him, well, we don't have electronic devices which can really manage to capture images from electron where the dynamics are extremely fast. We need switches of the order of micro to sub-microseconds. We have to capture the response of the unpaired electron if you want to do pulsed NMR, pulsed EPR, with capture speeds of the order of several megasamples per second. So we may have to wait for the electronics availability of electronic components switches and acquisition systems and fast computers in order to really do something that the NMR people are doing it easily now. So there will come a time where we will be able to mimic what we are doing with the nuclei in the case of unpaired electrons. And hypoxia regions, incidentally, are 3 to 4 times more resistant to radiation. That is one of the reasons that when a radiation or chemotherapeutic uh, regimen is applied to a cancer patient, apparently the cancer tissues are killed by radiation or removed by chemotherapy, but the core still remains pretty resistant to treatment. Then after about 6 months or 12 months, the tumor starts regenerating and regrowing again. In many cases, 80% of the cases, unless the surgical removal is absolutely complete, the tumor pops up again and starts growing again. But if we can somehow remove the hypoxic core or oxygenate the tumor very well, then it is possible to make the radiotherapy and chemotherapy very efficient, sometimes almost 95% efficient. And therefore, it is important that we must be able to non-invasively look at oxygen concentration in tissues and then start planning the irradiation with electron beam or X-rays or gamma rays. When these tissues are properly oxygenated, then it's easier to remove them more effectively. You can see normoxia, the tissues are compact, whereas when there is a hypoxia or anemia, tissues are a little bit loose, and then this hypoxia-inducing factor 2 is encouraged, and then you have cell proliferation, angiogenesis, metabolism, metastasis, and chemo and radio resistance builds up. And this is again a summary that metabolism is affected, generation of red cells from the stem cells is also affected, differentiation, cell death, angiogenesis. Tumor cells and normal cells have a slightly different morphology. Normal tissues are here where the blood supply, which brings the oxygen to the tissue, is pretty efficient. In the case of hypoxia, the cells are not compact. Large number of repair happens on the blood vessels supplying to these tissues, and there is a lack of oxygen, sufficient oxygen. Incidentally, this is another reason where the COVID damages our lungs, because it keeps the lung completely repaired. It's not able to take the oxygen transfer from breathing into the hemoglobin, thereby reduces the oxygen availability to the brain, and very soon it impairs the whole system. So hypoxia is a dangerous thing. In fact, today there was an article in the Hindu which says you can go and buy a pulsed oximeter, which you can clip onto your fingers and monitor your saturated PO2, and that is a very good indication whether there is COVID infection or not. And these are about 2,000 rupees. You can buy them online. And so they are advising that people should buy a pulse oximeter, which uses the infrared light absorption of the hemoglobin to quantify the oxygen content of blood cells. So hypoxia is a dangerous thing. And in the case of tumors, it produces high resistance for radiation killing. And therefore, it is important that we should be able to monitor the oxygen concentration in tissues. But if it can be done in a non-invasive way, it will be good, because anything you do by way of poking the tissue, by putting an electrode inside or oxalate electrode, etc., will damage the tissue, and it is invasive. If you want to do non-invasive oximetry, it must be a spectroscopic technique, but unfortunately, infrared will go only for a few millimeters. We would like to have something which will penetrate the whole body, image the tissue oxygen in an indirect way by way of looking at the relaxation of electrons. Unfortunately, we don't have unpaired electron in the system, so we have to inject a stable, non-toxic electron system into the living body, and then later on do the same thing as we do in MRI by way of putting in a magnetic field, applying gradients, and looking at encoding of the space in terms of frequency. So tumor hypoxia I already talked about. EPR imaging, of course, needs free radical. Natural concentration is extremely low. So what then is the EPR imaging, and why do we need it? And already I talked about it. Hypoxia must be a very important thing in physiology, and no wonder that last year the Nobel Prize for Physiology and Medicine was given to Spencer Radcliffe and William Kaelin for working on research as to how the cells sense and adapt to oxygen availability. Now, here are real examples of tumor progressing with respect to radiation as well as surgery, that those which are having oxygen availability, they get killed quickly, whereas without oxygen, they survive a much longer time. This is now with oxygen, less oxygen. So, large number of experiments have been done to prove that hypoxic coats in tumors make it highly resistant, and all our efforts to kill cancer cells via radiation and chemotherapy fails. And ESR, as I said, is the only non-invasive quantitative method of monitoring PO2. It comes as a result of oxygen, which is a triplet ground state, two unpaired electrons, is a high T2 relaxant. So most of the EPR systems which are affected by dissolved oxygen is going to have a short relaxation time or a large line width. Whereas in systems where the oxygen has been completely removed, or in vacuum or degas system, the line width will be extremely narrow. Therefore, it is possible to do a T2 weighted imaging like they do in MRI to get contrast in ESR images, which can be with calibration used to produce oxygen maps, almost indirect oxygen maps. Now, what is the difficulty about imaging is that in MR, about 1 to 100 are used where you need extremely short pulses, because when you excite an unpaired electron system, the machine is onslaught with the pulse power, so there is a certain dead time before which you cannot see anything. Once you start responding, you lose about 500 nanoseconds. And then the whole FID will last only for about a microsecond or so. In ideal systems, maybe it can be longer. Therefore, you need ultra short pulses and systems which will have very low dead time, and ADCs, analog digital acquisition systems, which can acquire very fast signals within of the order of a microsecond or two. So all these electronic devices for fast switching, switching here, acquisition, digitization, etc., were not available commercially until 1993. NASA was using quite a number of these fast digitizers for wartime photography, and therefore we could get hold of some very fast digitizers from NASA during 92, 93, and we started doing a few experiments with them. When we were doing this in the pulse system, quite a number of people from Johns Hopkins and from Dartmouth and from Germany and Belgium, they were trying to do the CWESR, where you keep the frequency constant and slowly sweep the field. This is okay because even if the line width is extremely big, we can sweep several tens of gauzes to look at the spectrum, and then later on we can encode them in presence of frequency. So even then, most of the spin probes, stable spin probes that were available were basically nitroxides. These nitroxides are fairly stable, but they slowly get reduced in the human system, but they are non-toxic. One can put nitroxides inside animals and then do a CW or a continuous wave field swept kind of spectroscopy. But at that time, the gradients required will be so high with broadline ESR that the then founder president of Electron Society, Harold Schwartz, mentioned in one of the international meetings, there are only two things wrong with in vivo EPR imaging. There is nothing to image, and there is no way to image. Therefore, one has to take it as a challenge whether it can be done. Fortunately, these are the requirements. You need narrow line water soluble spin probes because we have to infuse the system with a probe, paramagnetic probe. Resonators must have low quality factor because high quality factor will have a large ringing time because it's got a narrow bandwidth. You need large bandwidth, low Q, and preferably it should be done at radio frequencies. Until 1993, all the ESR imaging were done at L band, which is about 1.2 gigacycle, at which frequency the penetration is only a few millimeters. So obviously, NMR has been doing extremely well at 300 megacycles per whole body, and therefore we suggested to the NIH that if we are building a machine, we will build it at 300 megacycles. We need ultra narrow pulses, therefore you need very fast switches, fast recovery preamplifiers. In fact, we ended up designing our own preamplifier. We had an engineer by name Rolf Schudin, who was an expert in electronics. He built amplifiers with very fast recovery. Then we also had analog digital converter done by an electronics group in NIH the digital electronics group. These are not commercially available. And then in vivo studies, we need narrow line, non-toxic spin probe. And fortunately, at that time, a company called Nycomed Innovations in Sweden came up with a compound which are based on triaryl methyl. Triaryl methyl is a derivative of triphenyl methyl, first synthesized by Goberg, a Russian who was settled in the US. And this was the triphenyl methyl, and he wrote a paper saying that I have discovered trivalent carbon because it is carbon surrounded by only 3 phenyl group. And he was so proud. At the end of the paper, this sentence appeared: this work will be continued, and I wish to reserve the field for myself. But nobody can do this these days because you cannot reserve a field for yourself. But then at that time, nobody thought that carbon will exist stably in the trivalent state, and he is the first one to synthesize triphenyl methyl. Later on, this company, Nycomed, which is also a pioneering company in doing NMR contrast agents, came up with large number of derivatives based on triphenyl methyl. Here is a compound which they labeled as OXO71, where a carbon attached to 3 phenyl, and all the protons in the phenyls have all been removed by sulfur, and all the OH and other groups are deuterated. So this is a per deuterated triple derivative. It has got a line width of just 50 milligauss, very narrow line. Unfortunately, this stays in the body for about 20 minutes, animal body, and gets eliminated completely through urine, and therefore it is a safe compound. We have tested also in many animal systems, monkeys, rabbits, etc. It's highly non-toxic, and therefore it's an ideal compound for in vivo infusion into the body, and we will have free radicals floating in the blood, which can now be imaged. And the line width of this line, which is 50 milligauss, can go up to something like 400 milligauss when it is fully oxygenated. And when there is no oxygen, it is 50. In between, it was found that the line width of this compound is absolutely linear with respect to the partial pressure of oxygen. And again, this is another justification of going to low frequency. This was L-band, which was originally used for continuous wave imaging of electron, and we parked it around 300 megacycle. There is also one more reason for doing 300 megacycle, because number one, the penetration is several centimeters, and also 300 megacycle is a standard animal imaging frequency in NMR. And therefore, it would be possible for us to compare ESR images with the 300 megacycle animal imager, for example, from Bruker Biospec, and also co-register NMR images and ESR images. ESR can give rise to oximetric images, while NMR can give rise to vivid anatomical details, and therefore one will be able to relate the ischemic and anoxic regions of the animal with respect to what happens with respect to oxygen distribution. This is our spectrometer. I must say here that this was built entirely by a team led by Nallathambi Devasahayam, an electronics engineer who joined me at NIH after having worked in IIT Madras for about 20 years. And he is a genius. Tell him something, he will think about it. Until he solves it, he will not rest. This Nallathambi Devasahayam is responsible for this 300 megacycle, 600 megacycle, and 750 megacycle multi-frequency radio frequency spectrometer, which is functional, working, and the only one of its kind in the world working at National Institute of Health at Bethesda. Now, how do we do the imaging? Well, the principle is identical. Apply the pulse to a free radical system, get the response, which is a free induction decay. Fourier transform, you will get a spectrum. This spectrum will become a profile when it is done in presence of a phase encoding or frequency encoding gradient. Once you have the profile, you can start rotating the gradient in a polar or an azimuthal grid and get projections, which is called the radon transformation. Then you can do an inverse radon transformation, which is called also filtered back projection generate the image. This is the original methodology of radon and inverse radon that was used by Lauterbur, who discovered the first MRI, and also used by Mansfield in Nottingham, Lauterbur, University of Illinois at Urbana-Champaign, who first discovered the NMR imaging methodology and got the Nobel Prize in 2003. The same methodology we can now adopt for electron. And then we have to do some kind of a weighting, relaxation weighting. So one can apply a pulse. This is the dead time. There is an FID coming down. You Fourier transform this, you will get the projection. And you can take several projections along the azimuthal or the polar angle to generate a two-dimensional image. you do the same thing after do a certain delay in acquiring the FID. That means there is going to be a T2 waiting, relaxation delay applied to the image. And those areas which are highly oxygenated will disappear fast. And those are highly not oxygenated or fully anoxic will stay for a longer time because its narrow line width is narrow. Line width and relaxation time T2 are universally proportional to each other. Therefore, one gets a relaxation weighting and you can end up getting a back projection. This is actually a X phantom, an X tube where the triple radical has been infused, and you can see a beautiful three-dimensional image at three different angles. This is now a little mouse sitting there. The tail vein has been carulated and OXO63 triple radical is infused through the tail vein and it goes into the body and immediately infuses throughout the system, artery system, in about 10 minutes. After 10 minutes, when you do the image, this particular OXO63 triple based radical completely distributes itself onto the liver and the kidney. What you see is a folded liver around the sternum of the mouse, and these are the two kidneys. And these are two different views, three-dimensional views of the kidney and liver of a mouse, which has been infused with triple radical, and a three-dimensional back projection image has been done. And then, as we now mentioned before, if you do a relaxation delay, and you can see this is the image without any delay, taking all the FID into account for back projection. And then this is after 50, 100, 150, and 200 nanoseconds of acquisition. And some parts of the image is disappearing. And you can see after about 150 nanoseconds, intensity of the kidneys have completely disappeared. Whereas the liver persists, in fact, it persists up to about 1 microsecond. Therefore, the liver is highly hypoxic. Its line width of the triple radical liver is very narrow. And one can really look at the relaxation time and then convert that into a color coding. And you can see here the liver is hypoxic with this kind of a low PO2, while the two kidneys are about 10 to 40 millimeters of mercury pressure. So here is a method whereby looking at the relaxation weighting of an ESR image, one can quantify after proper calibration the distribution of oxygen in a three-dimensional way. But unfortunately, what happens is when you do the simple relaxation of a T2, there are quite a large number of susceptibility artifacts due to relaxation being affected by the gradient, because the gradient also changes the frequency, and therefore the interference of various frequencies will be much, much higher in presence of a gradient, and therefore there is going to be a calibration problem in doing a T2 star weighting of oximetry. So we said we will go for an echo type of situation where you put a 90-degree pulse. This is an FID, then put a 180-degree pulse, and this is the echo. You might wonder why this gradient is always on. The whole time factor from the start of the pulse to the end of the spectrum is hardly 3 or 4 microseconds. There is absolutely no time for switching on and switching off the various gradients. So ESR spectroscopic imaging is always done in presence of the various gradients, and the encoded systems is acquired in presence of spatial encoding. And then one can do filtered back projection of the echo, and what you get is a wonderful oximetric image where you can see the uniformity of the oxygen is good, and also the so-called histogram and linearity of the oxygen is much better than looking at T2 star weighted imaging. And so we can now look at echo, Fourier transform, and filtered back projection images. This has been used for quite some time. Unfortunately, this T2 and T2 star images, which still depend upon a certain amount of relaxation time, which contaminates the quality and calibration of the oxygen. So is it possible that we can use spin probes irrespective of the line width, as long as we can latch on to a little bit of the signal immediately following the pulse? It is possible to encode this single point as a function of phase encoding gradient. So this is single point imaging or constant time imaging. What it consists of is apply a pulse. This is the dead time. The FID starts here. Simply concentrate on a given point at a time tau, constant time. So up to this time, anything that happens with respect to relaxation or gradient, whatever, is going to be identical. So there is no additional frequency on the top of what you're acquiring at this point. And then one can just look at the intensity of this point by applying various gradient on all the three axes. And what you will get is a phase encoded intensity of a single time point. It's called the constant time point because it is at a constant delay from the pulse. It turns out that the T2, which actually describes the line width of the system, no longer comes into the picture because we are now looking at a constant time. The only thing that happens with respect to creating this echo is the gradient and therefore the position of the spin in presence of the gradient. And what you can do is Fourier transform the space encoded signal, and what you get will be an image, and this image will be not affected by the line width of the spin probe. And you can see some artifacts which comes as a result of T2 weighted images are completely removed in single point imaging, and what you get is a faithful reproduction of the distribution of the spin, because as the gradient becomes larger, as you go far away from the center of the K space, you try to get a large number of artifacts coming in T2 weighted images, whereas in a single point imaging, you get absolutely reproducible, faithful images. And therefore, and then what all you have to do for actually bringing in the relaxation is take a single point, generate an image, take a single point here and generate image, take a single point here and generate image, and it is possible now to generate a series of single point images. The only thing is, as you go far away from the pulse, there will be a frequency change, and therefore the view will go on decreasing. There will be a zoom in effect. We can always scale it back to the same area, and you can see, for example, these are 3 tubes. Single point imaging, as this is the echo, the single point, and single point imaging is very good in quality. And as a function of delay, you are zooming as if you are now going with a microscope and zooming the picture. Here is an example of single point imaging, the integrity of the single point imaging. Here is a phantom, and the image taken in MRI, and this is the image taken in ESR, and the correspondence is incredible. The resolution here is 300 micron. We could go a little bit more also, up to about 110 micron we can go. And you can see this is the MR image of water in that. This is the MR image of the spin probe in the same probe. And you can see even along a certain line, the power density remains very uniform. And therefore, this kind of a K-space, fully phase encoded Fourier transformation, since most of the intensity is in the center of the K-space, which is gathered at low gradients, what you get is a beautiful, uniform, faithful intensity throughout the image, which is very important for quantifying the relaxation time and oxygen. And this is an example of how beautifully linear 4 different tubes containing 0%, 1%, 2.5%, and 5% oxygen, single point imaging, and then looked at as a function of relaxation delay, one can really get resolution of about 0.2 millimeters of mercury. This is one of the best images that ever seen in literature so far. Here is a C3H mouse, which has been tail vein cannulated and infused with the tetracycline radical. And it is placed in such a only the abdomen and the legs are inside the coil. This is the SCC tumor, squamous cell carcinoma tumor, induced into one of the legs. And this is normal leg, this is the tumor leg. One can do a 3-dimensional spatial imaging of the spin distribution. And then do oximetry. This is spatial images which are sliced every 2 millimeter. And then in each one of the slices, one can look at relaxation time and look at oxygen distribution. What you see is a dark blue areas are hypoxic zones. And you can see in the case of the normal leg, the density of oxygen, PO2, remains between 40 and 50 millimeters of mercury, while there are very, very nice heterogeneous hypoxic spots inside the tumor, and that are given by this color coding. Another interesting thing is, we said that if the tumor is not properly oxygenated, it is not properly killed by radiation. And therefore, it is possible for us to do the radiation killing after making the tumor oxygenated. And here is a case where this is the same as the previous mouse, different experiment, of course. Here is the tumor leg, and you can see a very low oxygen of the order of 0 to 10%. Then a funnel was introduced into the nose of the mouse, and it is allowed to breathe carbogen, an industrial gas which has 95% oxygen and 5% carbon dioxide. This is actually used by divers who do deep sea diving in oil rigs, etc. And this is supposedly very good when they go way down in under the sea with high hydrostatic pressure. This helps the lung to react better. Therefore, this is the one which is introduced into the nose of the mouse. It is allowed to breathe for 20 minutes and the tumor gets oxygenated. From something like 0 to 10, it goes right up to 30 millimeters of mercury. And now, at this point in time, if we irradiate with radiation, the tumor cells will be killed much more effectively. Now we have talked about we talked about single point imaging. Single point imaging also can be made into an echo situation to latch out to a particular point, go to a point which is exactly juxtaposed with respect to a pi pulse, and then another conjugate point, another conjugate, etc. So it is possible to have a series of reflection, refocusing pulses, and choose time points in this FID where not only the intensity will be T2 weighted and not T2 star, because we have an echo coming in, all inhomogenities and T2 stars are focused, and at the same time, because of the encoding duration and the presence of gradient and its reversal, it turns out all the images will have identical dimension. So here, single point imaging, echo based, T2 weighted, with no need to resize the image. This is, of course, patented both in Europe and USA. And you can see the images are superb. These are oxygen images, uniformity is incredible. And what see the histogram, very nice. So this is now T2 weighted echo-based single point imaging. This was patented both globally and in USA about 6 years ago. Now let us go into an interesting thing, which is the indirect imaging, which is also called Overhauser imaging. Here we are using the electron to generate strong images in NMR by polarizing the nuclei, by transferring polarization from electron to the nucleus. This transfer of polarization is via the so-called nuclear Overhauser effect, first suggested by Overhauser. Nobody believed him. His paper was rejected initially and later on accepted, and he actually received a prize from Bill Clinton on the National Medal of Science for his discovery of Overhauser effect. This is now a big rage in NMR imaging because one can really enhance the nuclear imaging sensitivity by 3 or 4 orders of magnitude by transferring polarization from electron to nucleus. So this is actually an indirect imaging because when you're transferring polarization from electron to nucleus, you have to saturate the electron resonance. Saturation of the electron resonance will depend upon how narrow or how broad the electron line is, because you're going to burn a hole in the spectrum of electron distribution. And therefore, in situations where the oxygen is too much in an area, the electron resonance will be so broad that your saturatability of the electron line will be very difficult. In a situation where it is very narrow, it is easy to saturate with the given power of radio frequency. Therefore, one can use this incoherent transfer of magnetization from electron to nucleus to enhance the signal of the nucleus. In such a way, you can see here is an Overhauser imager. This machine was built for us by Philips in Hamburg. It does NMR at 15 millitesla. Even your credit card will not be affected. This is a air-cooled open magnet working at 15 millitesla. At 15 millitesla, it's actually 1500 Gauss. At 150 Gauss. In 15 millitesla, the frequency of proton resonance is 600 kilocycles. Lower the field during electron resonance to 7 millitesla to 200 megacycles. So 200 megacycle electron spin resonance, saturated at 200 megacycle. Transfer of polarization will take place into the proton and now do a regular NMR with the usual gradients, etc. And what is the situation? Situation will give you NMR images which are weighted by how the magnetization could be transferred, transfer being very high in hypoxic zones and transfer being extremely low in not so much oxic zones. So oxygen density matter in the term of the extent of Overhauser enhancement. And you can see here, this is the image taken at 700 kilocycle without any electron irradiation. You can hardly see. Signal noise is almost 2 to 1. When you do the same thing under the same magnetic field, but transfer polarization from electron to nucleus, you see the image of the mouse, rat actually. You can see the heart, you can see the descending aorta, even the lung. Everything is so beautifully visible, all because of a 1,000-fold increase in intensity, which is brought about by a transfer of polarization from electron to the nucleus. And these are phantoms, different concentration of the aqueous solution. This is actually 2 millimolar, this is 4 millimolar, And then after saturation of electron to proton, we can see different oxygen. This is 9.5% oxygen, 6.5% oxygen, 3.5% oxygen, 0% oxygen. And this is the oximetry brought about by indirect electron spin resonance. In other words, transfer of electron polarization to nuclei via the nuclear ORS effect, which depends upon the line width, which in turn can be quantified in terms of the oxygen in the environment. It's a very interesting experiment. Here is a rat sitting here at air for about 45 seconds. Beautiful oxygen. Means the intensity is proportional to oxygen. Now it is allowed to breathe only 9.5% instead of 20% oxygen. You can see a reduction in the oxygen. It is again breathing for about 6 minutes at air, which is 20%. You can really brightening up. Back to 9.5%. So it is highly reproducible, and one can use this for quantifying the oxygen in the body. In fact, about 2 months ago, when the COVID-19 hypoxia was raging through the United States, the FDA chief of United States, Steve Hahn, who was actually a colleague of mine from National Institute of Health, and I told him that why don't you put the COVID patients in a hyperbaric chamber? A hyperbaric chamber is the one in which hyperbaric chamber is the one in which there will be a high pressure of oxygen, and one can get increased oxygenation of the body, and that's what I suggested. Steve Hahn suggested it, and all right.
Yeah.
So this is a nice example of indirect imaging of electron through ORS effect. I'm going to skip through this because I have hardly 10 minutes to finish. And so with this, we have been able to do a lot of work. And finally, coming to co-registration, now that the machine built by us, which is on the left-hand side, can produce gorgeous images at 300 megacycle and also oxygen maps. And it's this is the gantry in which the mouse will sit. This whole thing can be placed into a larger gantry, and that thing will go inside a Bruker biospec machine. So without moving the mouse from its relative position in the coil, we have a coil which is tuned at 300 megacycle, and it will be something like 1.5 millitesla, 15 millitesla for ESR, and it will be something like 7 Tesla for LMR. So the coil is tuned commonly for ESR and LMR, and one can really put this inside the ESR machine, get the oximetric image, and then put it in the LMR, get the anatomical image. And apart from anatomical image in NMR, you can do diffusion weighting, blood volume, blood flow, all sorts of different functional imaging. And then you can compare the various contrast with respect to a particular functional imaging quality with oxygenation. And so EPR, MR, and as well as magnetic resonance spectroscopic imaging is what we do. Here, for example, is the SCC tumor on a mouse where the concentration remains constant, whereas the oxygen fluctuates. There is a professor in Duke University, Durham, Mark Dewhurst, who has been working on the cycling hypoxia theory, and he wanted a real proof because in all these cases, he has to kill several mice and then do biochemistry to say hypoxic and not hypoxic and how it fluctuates. Whereas in the present case of having a mouse live in the magnet, and repeatedly we can use the mouse today, tomorrow, day after. So without killing a bunch of mice and do the whole possible takes about 4 or 5 mice for reproducibility and do the whole hypoxia reactions in the mouse without sacrificing any mice. When we emphasize this in a particular conference, pharmaceutical companies were very highly interested because when they are trying to do some kind of a drug, they start with 500 mice to humans as a model with mouse. They start with 500 mice, and then 10 mice are killed on the first week, on the second week, and then finally by the time they reach about then 10 more mice is killed on the second week, and then finally by the time they reach about third month, all the mice are killed. Loss of mice. So with this kind you can see there is a large number of loss of mice. Or some kind of a whereas with this kind of a oximetric kind of imaging or some kind of a biochemistry that can be done without killing MRSI, it is possible to avoid a large number of mice being sacrificed. It's also possible to have oximetric image compared with anatomy, blood volume, apparent angiogram, arterial spin labeling, all sorts of functional images, apparent diffusion correlated, arterial spin labeling, all sorts of functional images can be correlated to the physiology that happens as a result of the well-oxygenated tumor. Here you can see normal mouse with a well-oxygenated tuber, you can see using ultra super paramagnetic iron oxide, which will kind of give rise to a dual image with USPO and without USPO. You take the difference, you get a blood volume. And you can see as you go from mildly oxygenated tuber, the blood volume comes down, and poorly oxygenated, the blood volume completely gets reduced. And the same sequence of blood volume corroborates with the kind of highly oxygenated tissue, about 30 to 40% oxygen, something like 20% oxygen, almost 0% oxygen. So, ESR oximetry corroborates with blood volume very easily and very nicely without sacrificing the mice. This is now dynamic nuclear polarization, the kind of work Professor Chandrakumar is an expert in. He's been working in DNP and hyperpolarization, I believe, for about half a century, if I am correct, right from his PhD thesis. This is the question of transferring polarization from electron to proton and trying to look at enhancement, hyperpolarization. And here is a spectrum of urea, which is taken at normal concentration. 7.5 ppm is at chemical shift. It is taken 65 hours to do carbon-13 spectrum in natural metals. That means something like several thousand spectra co-added, signal averaging. The same urea solution, when do under hyperpolarization condition, in 1 second, give rise to a spectrum which is here. You can just compare the signal-noise ratio. Therefore, hyperpolarization is another very interesting thing about it is hyperpolarization can produce such a difference in population of the lower and upper level in the case of a spin-half system that once polarization happens, you don't need a high-frequency spectrometer. You can use a novel 60 megacycle spectrometer and do all your experiments without any problem of signal-noise ratio. So hyperpolarization actually alleviates the requirement of extremely highly expensive high-frequency spectrometers, NMR spectrometers. Of course, once you polarize, magnetization, of course, decays with respect to its T1 and T2 relaxation. So all experiments must be done in the early days of early time after hyperpolarization. You can do MR angiography, perfusion mapping, molecular and metabolic imaging, etc. And you can look at various metabolic fates of pyruvate under oxic conditions, hypoxic conditions, etc. by doing the tuber inside an NMR machine and then looking at various chemical shift imaging. Alanine image, oxaloacetate image, acetyl coenzyme image, and all these depending upon the kind of condition of physiology, transamination, carboxylation, oxidative decarboxylation, reduction, etc., relate to different products. And one can monitor that non-invasively in a live animal. This is examples of treatment of, for example, here is now areas of different oxygen density. This is oxygenated, somewhat oxygenated, hypoxic zone. These three zones may have different concentrations of lactate, different concentrations of choline, creatine, etc. And therefore, you can correlate what happens to the physiology under various oxygen conditions, oxygen concentration conditions. Again, non-invasively, this mouse after about a couple of days will still be roaming around in its cage. We are not killing anything. These are, for example, mice's prostate cancer images, proton image, lactate image, alanine image, pyruvate image, bicarbonate. So you can actually tune the spectrometer for a particular metabolite and look at its distribution after hyperpolarization. The signal-noise ratio of these signals are extremely good because of the hyperpolarization technique. Well, I'm going to skip everything here and finally want to say something that this particular way of imaging electron is having a large SAR. The amount of energy dissipated into animal is very high because the pulses are at 500 or 400 watts and the pulse width is about 10 to 30 nanoseconds and therefore a large amount of energy is dissipated into the body. It is possible now to do CW, the conventional CW imaging, in which case what we do is we do a sinusoidal magnetic field and within one sinusoid, one half of the sinusoid, we can rotate the gradient and then you can collect the whole profile in a very short duration at very low power. And so by rotating the gradient and also using a sinusoidal field, it was possible for us to generate images under 1 millisecond for 2D, 1D, and 50 milliseconds for 2D and 3 seconds for 3D. The beauty of this rotating gradient and sinusoidal field is that it can be done very rapidly. Because it is CW, the kind of power we use is only of the order of milliwatts. And this is going to be the way that we are going to address EPR imaging in large parts of the human body, like, for example, elbow or head and neck with surface coils, etc. And this has been again patented, both European and global patent has been done on this rotating gradient and sinusoidal magnetic field to generate back projection images from electron spin resonance in larger systems in times of the order of a few seconds, like a 3D image of 64 by 64 by 64 pixels is of the order of about 3 to 4 seconds. And therefore, this will be extremely low power and will be accepted by FDA as far as SAR is concerned, specific absorption rates are concerned. And this is now being further developed using digital signal processing circuits and array program, gate array, DSP systems. So I wanted to just finish with some recent progress. Recent progress is reduction of specific absorption rate using something known as stochastic pulses or pseudo-random pulses, as well as partial K encoding. This is actually correlation spectroscopy, where you disturb the system with a noise pulse or a Hadamard pulse, and you can get a certain response which you correlate with the pulse itself, and you can generate FID and then go back to spectrum. These Hadamard pulses and specially designed pulses which are used in cell phone communication systems, which are called spread spectrum sequences, it is possible to generate images at extremely low power. And we have done some work using chirp pulses and Frank pulses and leading to images which are, this is the strong pulse, this is chirp pulse, and this is Hadamard transfer. So we are able to generate images at 250 milliwatts as against 250 milliwatts, 100 times or 1000 times less power. And this is now under progress. And with this, I'm going to conclude that the images with very good signal noise ratio can be obtained with 35 dB isolation between transmit and receive using Hadamard transform and correlation spectroscopy. The future plans are scale up large resonators, CW rapid scan, traveling wave antenna at low power for large size of body. This is being done for NMR at ETH. Compressed sensing, where the partial K space can be manipulated. Then real-time dynamic pharmacokinetics and dynamic oximetry can be done. Frank pulse and Hadamard, that's what I told at the end. And hyperpolarized metabolic imaging co-registered with oxygen, giving rise to some idea about what the hypoxia does to the tumor, what is the tumor physiology changes. And then the spectroscopic images gives us a clue as to what happens to the so-called drugs and the corresponding reactions from the drug. So let me just thank my co-workers, James Mitchell, the boss of the radiation biology, myself, visiting fellow. Murali Krishna is the principal investigator and he is a distinguished alumni of IIT Madras from 1919. Dr. Murugesan, again a former student currently in Chettinad University. Nalathambi Devasahayam, the electronic genius who helped us with all the development. And Tom Pohaida and Randall Pursley are digital signal processing experts from the National Institute of Health. Kostal Iniak is a microwave and RF instrumentation expert from Poland, but he is settled in USA. Ralph Shudin, again, is a genius who worked for Varian Associates, but an expert in NMR and ESR. Without these people's help and advice, we would have been nowhere. They are extremely good and very dedicated. And two postdocs from, one from Tokyo, other from this spelling mistake, Yokohama. Currently, he's a senior scientist in Tokyo. He's a professor at Hokkaido. These two people did all the animal work, extremely good at handling mice and then handling them with respect to LMR, ESR, co-registration and computation, etc. They will work for about 19 hours a day and sleep only for 5 hours. Tremendously productive. So with this, let me thank all of you for your patience in listening. I have skipped a few portions because I am a very, very poor estimator of time required for a talk. But generally, the idea I want to convey is with proper approach, everything is possible. If there is a good support from the funding authorities, we have spent a lot of money in building this machine and there was no dearth of funding. In fact, you can order a component at 5 o'clock in the evening. The component will be on your table at 9 o'clock in the morning. That's the kind of fast ordering of chemicals and components. Everything was available, and so we could accomplish it in little time. This is now end. Thank you.